So we got another example. This is one of the more complex examples. Maybe the most complex that you'll get, but it's not bad at all. If we follow the same steps that we've been following. So, and maybe remembering a little bit of geometry. A 2-meter tall boy is roller skating away from a 5-meter tall lamppost at a constant 2 meters per second. So this little dude here, he's just running away from the light, like I'm leaving, Mom. And he's going at 2 meters per second. How fast is the boy's shadow length changing? And then part B, how fast is the tip of the boy's shadow moving away from the lantern? All right, I'm going to draw a simplified version of this picture because we have similar triangles here where, well, this is 2 meters because that's the boy's height, and this is 5 meters, right? Because it says 5-meter tall lamppost and a 2-meter tall boy. Okay, and those don't change, so I can label those. That's perfect. Those don't ever change. What does change? Well, I know that changes. I'm going to call that x. That's just the distance from the boy to the lamppost. And then y is the distance of, or the length of the boy's shadow. Ooh, that's what I need, right? How fast is the boy's shadow length changing? Okay. So that's important there. And then the hypotenuse is also changing. That's growing and growing and growing. So that hypotenuse is changing. This whole side is changing, but there's 2 parts to it. Same with this, I guess. There's 2 parts to it. But it doesn't ask anything about the hypotenuse. So maybe this part is redundant. I'm sure it's redundant. I've done this problem before. Okay. So what do I know? What do I know? So I gotta draw my picture and label all the parts that are changing. So that's maybe step 1. Maybe write that down. Draw a picture and label all the pieces that change as variables. All the pieces that don't change, you can label them with their values. So we're given this 2 meters per second. What is that? The boy is roller skating away from the lamppost at 2 meters per second. So dx dt, that's going to be the boy's speed, right? The rate at which x is changing, which is the boy's distance away from the lamppost. And then dy dt, that's just the length of the shadow, right? Or the rate at which the shadow length is changing. So there we go. We have our meaning written down. What else? dh, that's just the I guess the distance between the actual light and the tip of the shadow. That's not what it's asking. From the lantern, I would consider that bottom part the distance from the tip of the shadow to the lantern. I'm not going to say the hypotenuse. We could find that, but I'm not going to do that. So, what do we have? Okay, now let's write down what we know, right? Dx dt, that's going to be dx dt, that was the kid's speed. That's a constant 2 meters per second, and it's positive because this is growing. We also, well, dy dt, we don't know, but we're looking for that when, it doesn't say, when, always. So maybe this is increasing at a constant rate also. This is a constant rate, so this will probably, hopefully, be a constant rate. I don't know, maybe not, I don't know. I guess if they don't give us a value, then it has to be. Is that all we need, right? No, it's not. We need a primary equation, which means we need to be able to relate our 2 variables. How the heck am I going to relate x and y? That's the main question. That's maybe the trickiest part about this problem. So how do I get an equation that relates x and y? Well, this is the part where you have to use geometry. These are similar triangles. This large triangle is a similar triangle with this small triangle, right? Because by angle, we definitely know that these 2 triangles share that angle, and they both have right angles. So by angle, these triangles are similar. So that's what we're going to use. We're going to use a property from geometry that says similar triangles have proportional sides. I think that's what it says. I don't know. Big side over the big side. This is just x plus y. So we have 5 over x plus y. And that is proportional. This is just from geometry. Big over big is equal to the small over small, the corresponding small sides. So 2 over y. So there's our equation. I can cross multiply and simplify this up a little bit. I'm going to do that because it becomes a lot easier if I do. X plus y, distribute, I get 2x plus 2y equals 5y minus 2y minus 2y. That goes away. We get 3y equals 2x. And that, my friends, is the primary equation. So now I'm ready to go. Whew! Lots of stuff. Lots of stuff. It's important to be organized, though. Look at that. It's all nice and neat. You label things so you don't forget what the heck they are. Primary equation. We got the dx dt, the dy dt. We know what those are. And I think we're ready to go. Since we have a primary equation, we can take the derivative of it using implicit differentiation. Remember, we have to do or use the derivative with respect to t, time. So that means we get 3 dy dt equals 2 dx dt. And what are we solving for in part A? How fast is the boy's shadow length changing? Oh yeah, we already said the shadow length is dy dt, or the rate at which the shadow length changes is dy dt. So here we go. We're solving for this. So I'll plug in what's dx dt. Dx dt is 2. So I have 3 dy dt equals 2 times 2. That's 4 divided by 3 divided by 3. So dy dt equals 4 over 3 meters per second. So that's the answer to part A. Sweet. What about part B? Part B. How fast is the tip of the boy's shadow moving away from the lantern? Oh my goodness. Oh my goodness. So let's think about this. Say we have just this boy, and we're just like we have a camera, and it's zooming into the boy, or I mean it's following the boy. So it's pretty much the boy is staying in a frame of reference, but the boy's moving. The shadow would keep growing, right? Because the camera is also following the boy as it moves. Like the boy's over here, the shadow's even longer. The boy's over here, the shadow's even longer. The shadow is growing at its own rate, right? It has its own rate. But this distance is growing at its own rate as well. We know that. It's 2. So when it's asking how fast is the tip of the boy's shadow moving away from the lantern, well, we have to take this rate and add it to this rate because they're both changing at different rates. It's like if you could throw like an 80-mile-an-hour fastball, all right, and like in space, we're thinking about in space where there's no air resistance. If you could throw an 80-mile-an-hour fastball, good for you. That's pretty good. Never mind. So if you could throw an 80-mile-an-hour fastball just when the ground isn't just on flat ground when you're stationary, then you hop into a car that's going 20 miles an hour and you throw that 80-mile-an-hour fastball, it's going to be going 100 miles an hour. You add the two rates together. Same with this. We have this growing at a certain rate and this growing at a certain rate, so we add the two together to get the rate at which that tip of the shadow moves. So part B is just 4/3 meters per second plus, well, that was that rate, adding it to this rate, plus 2 meters per second. Plus 2 meters per second. And that's just 4/3 meters per second plus, what is this, 6 over 3. I don't know why I keep writing meters per second. Maybe it's just a habit. 10 over 3 meters per second. That's just about 3.3 meters repeating. No, exactly 3.3 meters per second. So that's nice. There you go. That's part B. And part A, this is like 1.3 repeating meters per second. And that's it. I'm going to be done now. Good day, sirs and madams.